So how does radiocarbon dating work? Well, in the atmosphere, a neutron from radiation will sometimes collide with atoms. An energetic neutron could hit an atom of nitrogen, and when you look on the periodic table, nitrogen has 7 protons and 7 neutrons, a molecular weight of 14. Well, that neutron might hit the nucleus of the nitrogen atom and knock out one of the protons. Right? The weight will stay the same because you're adding one and subtracting one. So you still have a molecular weight of 14. But because a proton is ejected, now you only have 6 protons. So chemically, the atom behaves as carbon, but it has a higher weight. A normal atom of carbon will have 6 protons and 6 neutrons, or 12. So carbon 12 is what is a typical atom of carbon. Carbon 14 is what's known as an isotope. Isotope is any atom that has extra neutrons, therefore heavy molecular weight. And some isotopes, like carbon 14, are unstable, are radioactive. That means that they break down over time. So the carbon 14 that is produced in the atmosphere is then absorbed in the water, which is then picked up by the plants and the animals and us. So we have trace amounts of carbon 14 in our body right now. If any carbon 14 breaks down, it's replaced as we eat animals and plants and drink the water, etc. Right? So what that means is that when something dies, like this horse you can see here, and the bones are buried, what happens over time is that the radioactive carbon will slowly break down, where that proton will go back, that extra neutron will go back to being a proton, releasing an electron as well and a beta particle, and turn back into nitrogen gas. Right? So essentially, the longer something is in the ground, the less C14 it's going to have. And so if you find something and you measure the amount of C14 and you compare the amount of C14 left with the amount of C12 in that item, that should give you the date or tell you how old that substance or that bone was. Right? The longer something sits in the ground, essentially, the less C14 it will have. Right? So you can see, the half-life, what's called a half-life, is how long it takes for half of the C14 to break down. That's 5,730 years. So when it's first buried, a giraffe has all of the C14. 5,730 years later, it has 50% of the original. The carbon 12 remains the same. 5,730 years more after that, it has 25% of the original, half of 50, right? But it still has the same amount of C12. Right? So radiocarbon dating should be easy. We're going to see that it's not as easy as it looks. There's a little bit of a wrinkle in here that you guys are going to get to try your hand with. But essentially, C14 breaks down over time. The less C14 something has, the older it probably is. As it sits in the ground, the C14 breaks down. So what can you use this for? What can you use it on? Anything that is organic, made from organic material, or was an organic substance. Right? So you can carbon date wood. You can carbon date, so here you can see a wood in the hearth. You can carbon date seeds. You can carbon date bone. You can carbon date leather. You can carbon date shell, hair, blood residue, textiles and fabrics, paper, fish remains, insect remains, resins and glue, right? Antler and horn, right? Those are the things that you can date. Anything that is organic or made from something organic. Things that you could not date would be like things like pottery. Cannot be dated using C14 dating. Stone tools cannot be dated using C14 dating. Metal tools cannot be dated using C14 dating. They are inorganic substances. However, if you've excavated something very carefully, you might find something organic associated with the inorganic artifact. And if you date the organic artifact, you then get a date for the inorganic artifact by association. Okay. Are there any drawbacks? Yes, contamination can be a problem. You have to be very careful when selecting C14 samples, right? So we had in the trench where I worked in Turkey, no smoking policy, because if you're collecting one of these samples and some of the ash from your cigarette gets on it, you're essentially adding C14 to the sample, and you would get a younger date. You should not touch a C14 sample because oil from your hand will get on it. You have to be very, very careful in terms of contamination. Also, C14 dates are typically a range, plus or minus 40, 50, or maybe even 100 years. So you're not going to get a precise date. You're going to get a range. So C14 dating is the most commonly known scientific dating technique. When you ask people about archaeology and dating, most people will think of radiocarbon dating. So I'll give you another example of C14 dating and its use, and especially in terms of a subject that's pretty well known. This is the Shroud of Turin. Most of you have probably seen pictures of it. It's supposed to be the burial cloth of Jesus. They've radiocarbon dated it several times, but there's always some problems with it or some potential sources of error that people argue about. They typically date, when they date a sample, it's going to be destroyed. So you're not going to take a sample from the middle of the burial shroud. You take something from the edge. And when they have dated the Shroud of Turin, it dates to sometime in, I think, the 1300s AD. 1,300 years after the birth of Jesus. Now, some people think that the dates are a little younger because this edge of the cloth might have been repaired in later times where they added material to it to keep the fabric intact, thereby changing the date or adding C14 to it and changing the date. Now, if they were able to get a date, let's say they dated something more to the middle and they found a date, let's say 30 AD plus or minus 50 years, would that prove that it is authentic? It would not prove it's authentic, but it would prove that it dates to that time period. Okay, so let's take a little look at how C14 dates are calculated, and then also the problem with C14 dates. Let's just take a look at, let's say, a hypothetical atom. Let's say you have 64, well, not an atom, let's say a substance like a bone. In that bone, you have 64 atoms of C14, radioactive carbon. That's going to break down over time. After 5,730 years, half of them will have broken down. So you're only going to have 32 out of 64, half of the original. After another half-life, 11,460, you're going to have half of what remains, right? So half of 32 is 16. That would be 1/4 of the original amount. Another half-life, you could guess, you would take half of what's remaining there. You would essentially have 1/8 of the original amount. That would be 17,000 years. After 22,920 years, you'd have half of 1/8, or 1/16 of the original. In this case, it's 4 out of 64 atoms. 5 half-lives, or 28,000 plus years, you'd have 2 atoms left, or 1/32. Finally, 6 half-lives, 34,000 years, you would have 1 out of 64, 1 atom left of C14. Now, what would happen in the next half-life? Would you then have half an atom? you can never have half an atom. You would have no C14 left. It would all be gone. Right? And so one of the limitations on radiocarbon dating is that past 50,000 years ago, there's no C14 left in a substance to date it. So you cannot date anything older than 50,000 years old with radiocarbon dating. It has to be 50,000 years or less. And you can see it's an exponential decrease. You're taking half, then half, then half, then half. So it's not a steady curve, it's an exponential decline. So there are several limitations, right? You need a sample that's big enough, although the technology is rapidly improving and you can get dates from smaller and smaller samples. Contamination, as I said before, you have to be careful of. Association. You have to make sure that the sample is from a good archaeological context. You want to date something from primary context. You don't really want to date something from secondary context or tertiary context. Now, there is a problem. Right? There's a big assumption when you're looking at radiocarbon dating. Right? The assumption is all we have to do is figure out how much C14 is left, right? And then we can figure out how old it is, because C14 decays at a steady rate. But there's a big assumption within this, and it turns out this assumption is incorrect. Any idea what that assumption is? The assumption is that the amount of C14 in the atmosphere and the water and the plants has been constant through time. It turns out that that is not the case. So some periods, there was actually more C14 in plants, in animals, in the atmosphere. And because we assume that it decays at a steady rate and C14 levels have been constant, those dates we get are actually younger than the actual date, because that substance started out with more C14 than substances today. Now, this is a big problem, right? It means for a while that some C14 dates were inaccurate, were off. Well, what can we do to solve this problem? The only way to solve it is to use something that can be dated using radiocarbon dating, but then can be also dated with some other method. So can you think of any dating technique that we've already looked at that is looking at an organic substance that can be dated using C14 dating, but also can be dated using another technique? Hopefully you thought of dendrochronology. Right? Dendrochronology, the wood cores and tree rings can be dated to the year. Right? So if you know you have a tree that was cut down, let's say, and some of these tree ring areas go back thousands of years. Let's say you've got a tree ring core from 100 BC. Well, then you know it's from 100 BC. You can radiocarbon date it. You're not going to get 100 BC, but you're going to figure out how off it is. And once you figure out how off it is, and you keep doing that with other samples, you then can create a curve and a way to actually calculate samples so that you will get the correct date. Right? So there's an article in one of the try-it problems I have for you this week about a 27,000-year-old leaf that was proved very exciting for scientists. You might think, okay, what's so exciting about a 27,000-year-old leaf? Well, they knew it was 27,000 years old based on the sediments, but they could radiocarbon date this leaf now, and they can see how far off those dates are. So with radiocarbon dates, you again get a range. It would be something like 5,000, 5440 plus or minus 100 BP. We're going to talk about BP and BC in just a second. Okay, so how do archaeologists, when they get, let's say, the amount of C14 left in the substance, how do they then convert it into an actual date that's accurate? Let's take a little look. This was a big undertaking by scientists, but scientists had to put together a database of dendrochronology samples where the date of the tree was known and how much C14 was left, and the date that you got from C14 dating, in order to accurately adjust C14 dates that you get from a laboratory, right? So if you know, let's say, okay, this wood is from 100 BC, but we get a radiocarbon date of, let's say, 200 BC, then we know at that time period there's a fluctuation there, and we have to put it into our software, right? Okay, typically when you send a sample to the lab, they will not give you the date calibrated, right? Calibrated means that you're using all of that dendrochronology data to get the actual date. It's up to the scientist who gets those dates from the lab to then convert it and calibrate it using some software package. I'm going to show you how to do that. Also, they tend to give you the date in what's we call BP, not BC, right? BC are the calendar dates, right? Are the dates that we might see in the textbook. BP is before present. Essentially, it means years ago, right? Now, typically, we calculate years ago from, when we're talking about radiocarbon dates, from 1950, when radiocarbon dating was developed, not from the present day. But just for, for argument's sake, let's say we want to go back. Someone says, what was the date 4,020 years ago? Right? Well, the answer would be 2000 BC, because you would go 2020 years back to the year 1, and then another 2,000 years now into BC to 2000 BC. Right? So when we're getting to, when we talk about AD and how many years ago, it's pretty easy. If we say 500 years ago, 1620, right? If we say 600 years ago, 1420, right? But then when we start talking about BC, when we're talking about thousands of years ago, sometimes it's hard to conceptualize. So 10,000 years ago would be roughly 8,000 BC. Again, you're subtracting around 2,000 years to get to the year 1. You've got 8,000 years left. Okay, so that's one of the first steps that you have to use when you're calculating a date. But all that is doing, that is not actually calibrating. All you're doing is you're converting BP to BC. All right, so let's take an example. You're going to use this software called Calib. It's free software that's online. I'm going to show you how to use it in just a second. You guys are going to be calibrating 2 dates. Let me show you how to do this. You go up here to execute the HTML version. So online at this Calib program, they've got all of the dates that have been collected from dendrochronology, and they've got essentially an algorithm to help correct the date that you get from a lab. Right? So you go to the data input entry form over here. Right now, let's just we're going to just pretend here. We used 4,000 years ago, roughly 2000 BC. So let's put in 4,000 BP. Let's just say plus or minus 60. We're making this up right now. Okay, so if let's say we sent our piece of carbon, we're digging a site in the Middle East. We found a tree trunk from a hearth. We sent it to the lab. Lab sends us 4,000 BP back. We're like, okay, uncalibrated. All right, let's see how far that's off from what it should be. Now we enter the data. We hit calibrate. It compares it to a curve, right? And what we do is we look over here at 1 sigma, that's 1 standard deviation around the mean. We look at the relative probability. The highest probability is 0.899 over here, and the actual date is 2585. So the year 2585 BC to 2558 BC. Again, it's a range, right? Same with the BP range. Okay, so uncalibrated, our date would be roughly 2000 BC, right? It would be something like, 1940 to 2060 BC. How far off is it from the real date? It's about 600 years or 500 years off from the actual calibrated date. That's a lot. 500 years is a lot, right? So you have to calibrate your dates based on the information we know now. Otherwise, you're actually getting a fairly inaccurate date, right? Okay, so let's just take another one just so you can kind of see again. Let's say we find something in North America. We think it dates to the Clovis period. And we know that the Clovis period, let's say, is 12,000 years ago. We enter the data and we calibrate it here. Let's see. Actually, we gotta clear it. So here's how you clear the data. We go down and I entered it wrong. I entered 1200 years ago instead of 12,000 years ago. But still, so 1200 years ago would be about the year 800. But according to the radiocarbon dates, it would actually be around, you can see 0.8 here, around 773 to 893 AD. Right? And what you see here, this is actually the calibration curve, right? So you can kind of see the standard deviation around the mean, where most likely the date falls somewhere in this range, right? Okay, so this is how calibration works. So you're going to essentially take two dates. You're going to see what they are when you convert BP to BC. That's easy. And that's not calibration. All you're doing is you're figuring out, 3,000 years ago is what in BC. In order to calibrate, you have to enter it into the database so it can correct it, and you'll see what the date is there, right? Okay.